right, we are on 6.02 for pre-calc today. And this is going to be our intro to vectors. So we're trying a little different way today since my computer is giving me some problems. All right, so we'll start with talking about vectors, which a lot of you guys have talked about before in physics. So vectors have both a magnitude and a direction. Really magnitude and direction. Really important about a vector. So magnitude, which is just like your length, and they're going in a certain direction. Sorry if you hear Gianni yelling about something. Okay, vectors are represented by a directed line segment. And again, that's because they're going in a specific direction. So you see them, it looks like a ray. So it's directed in a certain direction, has an arrow, and those would be your points. When we name it by a lowercase letter. So it's denoted by a lowercase letter when we name a vector. And we can say if vectors have the same magnitude and direction, then they're equivalent. Okay, you'll notice too, I'm taking these notes on graph paper because there are some questions that we will want to use graphs for, but not the first couple, or not the first one at least. All right, so first question. Let U be directed by the line segment from P, which is 0, 0, to point Q, which is 3, 2. Let V be represented by the directed line segment from point R, which is 1, 2, to S, which is 4, 4. Show that U is equal to V. And sometimes too, we can show vectors with this little kind of ray-like shape above it. In order to show that we have these two equal vectors, we need to show two things: that they have equal magnitudes, meaning equal length, and equal direction, or the same direction. All right, so first let's focus on finding our magnitudes and showing those are the same. So first we're going to show equal magnitude. Now magnitude, we said, is length, and we know from geometry we have our distance formula to show length. So D equals the square root of the quantity x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. So that's how we find distance. Again, magnitude just means that they have the same distance or the same length. So if I want to find the length from P to Q, I'm going to find the distance of PQ. And to show magnitude of this vector, you show, it's like double absolute value bars. That means magnitude. So I'm going to take those 2 points for P and Q, and I'm just going to find the distance between them. So in geometry, you might have called one like x sub 1, y1, and x sub 2, y sub 2. If that helps you, feel free to do that. So we take our x sub 1, or x sub 2 rather, which was 3 minus 0 squared plus 2 minus 0 squared. So now I have 3 minus 0 is 3 squared, 2 minus 0 is 2 squared. That gives me 3 squared is 9 plus 4, which is the square root of 13. Now I'm going to find the magnitude of vector RS. So I'm going to use points R and S this time and find the distance between those 2 points. So again, you can write your x1, y1, x2, y2 above them if you want, or you can just go ahead and substitute right in. And then we'll simplify. So we've got 4 minus 1 is 3, 4 minus 2 is 2, 3 squared is 9, 2 squared is 4. Again, we get the square root of 13. So far we see that our magnitudes are the same. Those two are equal to each other. So we need to now show, so we showed they have equal magnitude. Now we want to show they have the same direction. Now to show direction, we're going to use our slope formula. So slope formula is m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So your change in y over your change in x. Be careful, a lot of times when I ask students what's the slope formula, they tell me y equals mx plus b. And y equals mx plus b is the equation for a line. It has slope in it. The m is the slope, and y equals mx plus b. All right, so now we'll find the slope of PQ. So again, I'm going to be looking at point P. Oops, you can't see. Point P and point Q, I'm finding the slope of. So I'm going to do 2 minus 0 over 3 minus 0, which just gives me 2/3. And then we'll find the slope of vector RS. So now I'm looking at point R and S. So change in y, 4 minus 2 over 4 minus 1 would give me 2/3. And now I have equal slopes. Therefore, my 3 dots mean therefore I know U equals V because, so they're equivalent because they have the same magnitude and direction. So they look different, they're in different spots, and that's okay. So if you pick one vector up and you can move it around, as long as it keeps that same slope and the same length, you can put it anywhere you want on the graph, and it can be equivalent to any other vector that has that exact same slope and that same distance, even if they're not in the same spot, as long as they have that same distance and the same slope. All right, now let's talk about component form of a vector. Okay, so a few things here. When you're in component form, the initial point is always at the origin. The initial point is at the origin. Okay, we also, by coordinatizing, the vector is going to be useful because then the vector can be uniquely represented by the coordinates of its terminal point. So you name them by their terminal point. So whatever point they end at. So if it ends at v1, v2, let's say, then vector v would be, we use angled brackets, we'd call it v1 comma v2. So that is called component form. So component form is when you put the vector so that its initial point is always at the origin, and then you name it by whatever the terminal point is. So if it starts at 0, 0, and then it ends, the terminal point is 3, 2, you would name it with angled brackets 3, 2. And the 0 vector is a vector with both its initial and terminal point. Initial, I've got like an extra letter in there. Initial and terminal points are at 0, 0. And that vector would be written just as 0, 0 with angled brackets. So really important to remember for component form, the initial point is at the origin and you name it by its terminal point. And you always use angled brackets, just like these are angled brackets as opposed to parentheses there. So now let's talk about our formulas for magnitude and just finding our vectors as well. So that's all for component form. Now we're going to talk about some formulas. So we're going to assume the initial point is P, we'll call that P sub 1, P sub 2, and your terminal point is Q, so Q1, Q2. So assuming that's true, a few things that we can say then. So we know that in vector form here, if we want to find the vector of PQ, we take the terminal point minus the initial point. And this is how we're going to get it into that component form. So your terminal point is Q, so we would take Q1 minus P sub 1, and then Q sub 2 minus P sub 2. So that would give you a new vector, let's say V1, V2, which is just your vector V. Okay, so really important to remember here, to put your point into component form, you're going to take the terminal point minus your initial point. And again, that is component form. All right, to find your magnitude now, we have a little bit of a shortcut. So again, you use those double absolute value bars here to show magnitude. And you would be doing your distance formula. So you would be doing Q1 minus P1 squared plus Q sub 2 minus P sub 2 squared. Now, since this point right here is your component form, and we said component form means your initial point is at the origin, then you would just be subtracting 0 from each. So instead of doing your distance formula, if you have it already in component form, you can just take V sub 1 and square that and add it to your V sub 2 squared. And that'll give you your magnitude, and take the square root of that. So that's, once you're in component form, you just take your two components here, square them, add them together, take the square root. Because again, this is representing your terminal point, which are these right here, and your initial point 0. If we subtract 0, you'd just be left with v sub 1 minus 0 is v sub 1. V sub 2 minus 0 is v sub 2. And a unit vector, it's like our unit circle has a radius of 1. Our unit vector has a magnitude of 1. So a unit vector has a magnitude of 1. So a lot of new information for us. All right, let's do, I'm going to restart here at 1. So at 1 says find the component form and the magnitude of vector v with initial point at -1, -4, and terminal point to -2. And put your answer in simplest radical form, SRF, simplest radical form, if appropriate. Okay, so first, let's work on finding our component form. All right, so to find our component form, you want to take your terminal minus your initial side. So terminal minus initial. So here we would take our terminal point is 2, -2, initial is -1, -4. So we're going to take our 2 minus -1 and -2 from right here, our terminal point, minus -4. And now 2 minus -1, double negative becomes a positive. Same thing here, and -2 plus 4, or 4 minus 2 is just 2. So this vector v in component form would be 3, 2. So what that means is it has an initial point at 0, 0 and a terminal point at 3, 2. So let's actually graph this just so you can see the differences here. All right, so if you wanted to graph the original, our initial points at -1, 1, 2, 3, 4, terminal points at 2, -2. So let's call that your P and your Q, right? So this is your Q is a terminal, P is initial. So it's going towards your terminal point. So that would be your vector PQ, the original one that was given. Now our new one in component form says it's called 3, 2. So I'm going to plot the point 3, 2. Anytime you're in component form, so with these angled brackets, your initial point is going to be at 0, 0. So 0, 0, your ending point is the point 3, 2. So I plotted that here. So this is your new vector v. Notice these are equivalent vectors. They have the exact same slope. If you go rise over run, up 2 over 3, up 2 over 3, and they have the exact same distance as well. So, and we're going to find that distance in just a minute. But I want you to see that they're equivalent vectors and we can write them in two different ways. And it's okay that they're not like on top of each other. It just means to be equivalent vectors, you have to have that same length and you have to have the same slope. So I could take PQ here and I can shift it up and over and it would lie right on top of there if I translated it over. All right, and then it also asked for the magnitude here. So for our magnitude, we're going to find that from our component form. So magnitude of V. So to do that, again, your initial point is 0, 0. Your terminal point is 3, 2. So you're just finding the distance between 3, 2 and 0, 0. So to make that a little shorter, we don't need to do the 3 minus 0 squared every time. You just take the first component here, which is 3. So we do 3 squared plus 2 squared and take the square root of that. And apparently I really liked 13 when I did these notes. So this is the square root of 13 would be your magnitude. So both of these have a distance of the square root of 13. All right, let's do another one just like that, just to practice since this is very new for you guys. So number 2, again, I want you to find the component form and the magnitude of vector v with initial point for -7 and terminal point -1, 5. Again, if you need to, put it in simplest radical form. And I'd like you to pause the video here, do exactly what we did in number 1, find your component form, and find your magnitude. Go ahead and do that right now, and then check back here. All right, so for your component form, again, you're doing terminal minus initial, so you should have had -1 minus 4 and 5 minus -7, so your final answer should be -5, 12. I want to see on your notes that you have shown that work of doing terminal minus initial. For the magnitude, you would be squaring -5 squared. Now, when you write that, make sure you put the -5 in parentheses squared. Plus 12 squared, again, show out all your work. So 25 plus 144 gives you the square root of 169, which is 13 again. So your component form, and this is your magnitude. Again, to find the magnitude, you're just squaring the first number, squaring the second number, add them together, take the square root. It's just the distance formula. Your initial point, though, is 0, 0, and your terminal point is -5, 12. And you could graph this component form by plotting the point 0, 0 and the point 5, 12, and you'd have an arrow going towards the point 5, 12. Okay, next we're going to talk about vector operations. So a lot going on with our vectors today. So for vector operations, first we'll talk about scalar multiplication and then scalar addition. So it's important to remember that a scalar is just a number. So if you want to multiply a vector by a number, you can just distribute it in and multiply it. So the product of vector v and a scalar, that's not it, scalar k, put my k too early, is the vector that is k times as long as v. Now, if k is positive, then when you multiply k times v, it will have the same direction as v. And if k is negative, then k times v would have the opposite direction as your original v. And then scalar addition also known as your parallelogram law, tells us the sum of u plus v, so of two vectors, is the vector formed by joining the initial point of the first vector with the terminal point of the second vector. And that's what you talk about more so in physics, the tip to tail setup. And u plus v is known as the resultant of vector addition. So again, if you had vector A and vector B, you would line those up tip to tail. So the tail of one goes to the tip of the next. So that's vector B, vector A, and then this would be the sum of your two vectors. So tip to tail, and that's how you would do your addition. All right, so for kind of your definitions here, and then we'll go into some problems. I know there's a lot of writing today. Definitions. Let's take u plus v if we're adding. So vector u would be u sub 1, u sub 2, plus vector v is v sub 1, v sub 2. You're just going to add like kind of your x coordinates and your y's. So you would add u sub 1 plus v sub 1 and u sub 2 plus v sub 2. If you're doing scalar multiplication, then you would take k times some vector u, so u sub 1, u sub 2, and you would just kind of distribute it in. So it'd be k times u sub 1 and k times u sub 2, and we'd still end up with those vectors in component form. So let's do a couple examples of those. So we're on number 3 now. So we'll do two different ones, and for both of these, for part A and B, let vector v equal in component form -2, 5, which means it has an initial point at 0, 0 and a terminal point at -2, 5. And vector w would be 3, 4 in component form. And then I'll have you sketch them too. So here's where you might want some more graph paper as well. All right, so first A, let's do 2 times vector v. So if we're doing 2 times vector v, we're looking at just v here. And we want to multiply 2 times that vector. So you're really just distributing that in. So it would become -4, +10. If we look at this graphically, just to see what's happening here, we would take, let's look at original vector v. So again, initial point 0, 0, terminal point is -2, 1, 2, 3, 4, 5. So we've got, oh, actually we're gonna need to, let's count by 2's here, because we're gonna need to get to 10. 2, 4, 6, 8, 10. So my initial vector then would be, this I'll count by 1's, -2. So 0, 0, and then -2, 5. would be our original vector v. And then -4, 10, so up here, that is my ruler, from 0, 0 still. That whole vector right here would be your vector 2 times vector v. So notice they're still in the same direction because we multiplied it by a positive scalar quantity. Scalar just means a number. And it's double the length. So original was here, but now it's the same direction, but now it's twice the length. So that's what's happening when you multiply it by a scalar quantity. And let's look at some addition, subtraction. So w minus v. So first of all, I could rewrite that as w plus -v. So it's addition. Or you could leave it as w minus v. And let's just go ahead and combine those. So our w is 3, and our v is -2, so we'd have 3 minus -2, and 4 minus 5. So for addition and subtraction, you're just combining those terms. I guess you couldn't see up here, sorry. 3 minus -2, 4 minus 5. And if we combine those, we would get 5, -1. Again, that's in component form. So let's take a look at the graph of this. So we've got, let's graph W, V, and the sum of these two. So W is the 0.34. So again, when it's in component form, your initial point is 0, 0. Terminal point is 3, 4. So that is vector W. V is -2, 5. So initial point 0, 0. Terminal point is -2, 5. So -2, 1, 2, 3, 4, 5. From 0, 0. And that would be your vector V. Now our new vector, when we do W minus V, is 5, -1. Again, it's in component form, so initial point 0, 0, 1, 2, 3, 4, 5, -1 should be my W minus V. So for that one, to get it set up into your addition, your tip to tail, V, you're taking the negative value of V, or you're multiplying V by -1, which is going to switch the direction that V goes in. Okay, so I'm going to switch the direction, and I'm also going to shift it over. Like I said before, equivalent vectors just mean it has to have the same direction. In this case, we're going to take the opposite direction, and the same length. So I'm going to just take this vector V, and I'm going to move it over here so that its tail actually is going to be at the tip of W. So I'm taking this whole thing and shifting it over, which will actually should bring me right from here to here. So switch the direction, and that would become your vector V. So notice when you're looking over here, it's tip to tail right here. W to V is tip to tail. And then the resultant is your W minus V. And we're not going to do a whole lot of that. We don't do nearly as much as you guys do in physics. For this course, really what I want you guys to be able to do is write your vector in component form, so terminal minus initial, find the magnitude, and be able to, at this point, multiply by a scalar quantity, and also be able to add and subtract. We're not going to focus as much on the graphs, more so just on the more the algebraic portion of it. But it's also important to understand it graphically. All right, and last thing we're going to talk about, which will come up a couple of times here, is our unit vector a little bit more. So far, all I mentioned was that a unit vector has a magnitude of 1. So a unit vector is useful when finding the n-coordinate, which has the same direction, but a different magnitude. So you can use to find a vector, a new vector with the same direction, but different magnitude. Of a given vector. All right, so to find your unit vector, what we do is we need to find the magnitude of that original vector. So let's say we have vector v. We would take that vector and divide it by its own magnitude. What that does is, so let's say your magnitude was 5 of v, then you're going to divide that whole vector by 5. So think about it, when you divide 5 by 5, you get 1. So a unit vector, we want to have a magnitude of just 1. So we're going to take whatever your vector is and divide it by its own magnitude. And that's going to give you a magnitude of 1. All right, I think we are on number 4 here. All right, so use the formula to find the unit vector of v, which is 4, 3 in component form. So to find the unit vector, we're going to first find the magnitude of v. So remember your magnitude formula, just your distance formula, but this is your terminal point and your initial point's at 0, 0. So you're really just taking 4 squared plus 3 squared, because 4 minus 0 is 4, 3 minus 0 is 3. And then we have 16 plus 9, which is 25. And there you go, a magnitude of 5. So now what I want to do is I'm going to take my original vector and I want to divide it by its own magnitude. So I'm going to take 4, divide that by 5, and I'm going to take 3 and divide that by 5. So this will be my unit vector of v. Now let's call that part A. Now, just for fun and to kind of show you why this works, I want you to verify that the unit vector now has a magnitude or a length of 1, because we said a unit vector has a magnitude of 1. So you just found a unit vector right here, we just found. So to do that, we took our original vector, we found the magnitude of it, and then we divided that original vector, the 4 and the 3, all by that magnitude of 5. So we got 4 over 5 and 3 over 5. Now let's find the magnitude of that. So we're finding the magnitude of that. So our original. So we're going to take the square root. Remember, it's component form again. So the initial point is 0, 0, and this is your terminal point. So all I have to do is take 4/5 squared plus 3/5 squared. All right, so let's do it without our calculator. So 4 squared is 16, 5 squared is 25, plus 3 squared is 9, 5 squared is 25, 16 plus 9 is 25 over 25. Add your numerators, keep your denominator, and 25 over 25 is 1, and the square root of 1 is 1. So it does, in fact, have a magnitude of 1. This right here has a magnitude of 1. That's our unit vector. All right, and the last part here, and this is the part that will come up a couple of times, it's really important, is I want you to find another vector, a new vector. Let's call this one W. That's in the same direction. This is what we're going to use unit vectors for the most. In the same, no, how did I spell direction? Same direction as V with a magnitude of 30. So once you find your unit vector, so we want to take vector V, we want it to be in this, same direction as vector V, but instead of having a magnitude of 5, which this one has, I want it to have a magnitude of 30. Right here. So to do that, first, we'll get this vector to have a magnitude of 1. So the unit vector, we know, has the same direction as the original, but it has a magnitude of 1. Once it has a magnitude of 1, now I can simply just use scalar multiplication and multiply it through by 30. So 30 times 4/5 3/5, in component form, and now I'm just going to distribute. So this is vector W. So I've got 30 times 4/5, so 5 goes into 36 times. 6 times 4 is 24. 5 goes into 36 times still. 6 times 3 is 18. So your new vector W would be 20, oops, sorry, you couldn't see that, 24, 18. All right, and then, I know these are long notes, I apologize, but for number 5, since this was a really important question, I'd like you to just do one more of those on your own. So find a vector, let's call it U, in the same direction of vector V, which is 2, -3, but with a magnitude of 5. So for this one, again, you're going to do the same way we just did the last one. First, find your unit vector of V. Once you find your unit vector, then you can multiply it through by 5. Pause the video and do that right now. All right, so you should have gotten for your unit vector, and I should see the work on your paper. So for the unit vector, you want to find your magnitude first. So the square root of 2 squared is 4, -3 squared is 9. So again, rad 13. And we'd want to divide the original vector by our magnitude. Now I can't leave, so my original is 2, -3. I'm dividing them both by radical 13. I don't want to leave radicals in the denominator, so I need to rationalize that. So multiply the top and the bottom by rad 13. So 2 rad 13 over 13. And -3 rad 13 over 13. So that is my unit vector. So I took my original vector, found the magnitude, which is rad 13, divide that by its own magnitude to give me a magnitude of 1. So here's my unit vector. But I want not just the unit vector, I want a vector in the same direction as this, but a magnitude of 5. So now I have a vector in the same direction, but with a magnitude of 1. So now I want to get a magnitude of 5. All you do after you find the unit vector is just multiply through by 5. So pause your video if you haven't done that yet. Go ahead and do that now. And your final answer, 5 times 2 is 10, rad 13 over 13. And 5 times -3 is -15, rad 13 over 13. So nothing else changes here. When you multiply 2 rad 13 over 13 times 5 over 1, you just multiply the non-radicals together. And that would be your final answer. And that is it for today. If you have any questions at all, please be sure to let me know. And pie out.